Okay, how do we change pH? I made a huge deal about pH. Gotta get it in the right range, gotta get it there. We have tools to do this, we got tools to that. Well, we change it with different types of amendments to the soil. We either put lime on it, which raises the pH, or we put sulfur, elemental sulfur, which will help lower the pH. There are other methods out there, but they are very slow and they're not going to have any type of effect that you would desire if you're trying to manage the situation. For example, nitrogen fertilizers have a net acidifying effect over time in the soil, but that process is much more lengthened out. And when we're trying to deal with a garden, we want quick changes. We want the conditions to be as ideal as possible as soon as possible. And we don't have to deal with 160 acres at our disposal. We have relatively smaller areas that we can change and manage to our benefit. And so some of these things would be way too expensive to do on a field scale, which would be elemental sulfur to effectively lower your pH. But on a garden scale, it may be the only way you can make your situation viable for a garden. And so that's why I'm bringing it up. So looking at this graphic, it's similar to the one I showed before with that diffuse double layer, if you remember that little brown rectangle. Somehow, we have to take out all these hydrogens. We got to take them out of solution because this is what is considered the pH of the soil, is measuring this area out here. When we measure that, we're not actually measuring the area that is on the soil particle, as I said. But if you remember that diagram, I showed a lot of concentrated nutrients right up close to the soil particle. And then as we got further away, there were fewer and fewer nutrients out there in solution. So here's a question. What do you think is going to happen if we neutralize every hydrogen ion in soil solution? But you look over here at the soil particle, and this is what's waiting. So here's the reserve acidity, which is on the particle, and the active acidity is what you're neutralizing. What's going to happen if you only neutralize what's in the solution? Yes, the reserve will revert to the active, absolutely. So when we are trying to neutralize pH, you are not only trying to attack what is in the soil solution, but you're trying to attack what will be in the soil solution, which is that reserve acidity. Because as you take these away, there's another thing to fill its spot. Soil nutrients like to go from high concentrations and disperse to lower concentrations. They like to spread things out. They have a bubble they like to keep. They don't like to be bumping into each other all the time. And if they have a choice, they move out. And so when we talked about CEC now, which type of soil is going to take more lime to raise the pH? Is it going to be a heavier textured soil that has more clay content in it, or will it be a more coarse textured soil that has less clay, more sand and silt in it? It's going to be much harder, or it's going to take a lot more material to neutralize that acidity for a clay soil than it will be for a soil that has less clay in it, like a silt loam or something with more sand in it. Because when we talked about soil texture and cation exchange capacity, the type of soil particle that contributed to CEC was clay or humus, organic matter. That is the ability to hold on to these nutrients. And so if you have clay, you have a lot more negative charges out there. I'll get to that in a second, Robert. If you have clay, with a lot of negative charges out there holding on to all this hydrogen, there's still the soil solution that gets neutralized, but there's just that much more that that clay particle has been holding on to that will now need to be released into solution, be neutralized, release more, so on and so forth, until you actually get it down. So that's what's going on. And your question is this due to minimal water holding capacity? No, it has nothing to do with water holding capacity. This is simply on the chemical level. Water is only facilitating the exchange of these particles going back and, or excuse me, the ions going back and forth. So completely unrelated to the water holding capacity, simply a chemical process. I think we had a question earlier from the Panhandle, and it was asking, is this related when you try to lower your pH instead of raise it? I referred to using sulfur as this disintegrating sulfur. It's elemental sulfur. And there is, the reason that's the case is because elemental sulfur is going through a mediated process with the microorganisms, which is unlike what happens with lime, which is strictly a chemical process. And another question, so there is no osmotic issue. No, there's not an osmotic issue because we're not going into tissue. It's simply there's water there, and once the water's there, these ions can just move back and forth. What is the profile of central Nebraska's soil? Is it more alkali versus acid? Thus, if alkali, would we not add lime? I'll have to look at that, but most soils, especially, I mean, we even have basic soils in the East. The only time we're finding a lot of acidic soils are under long-term crop production because it takes a lot of nitrogen fertilizer over time. Or if you get further and further east, and I'm talking past Illinois, out to New York, where they have a lot more rainfall and different parent material, it starts to acidify. I would imagine ours would be fairly close to neutral to slightly basic. And if they are slightly basic, you would not want to add lime to that situation. It would raise your pH further out of the ideal range. So if you're below 7 and you're acidic, that's okay. But once you get past the critical range, you're going to need lime to bring you up. If you're above 7, meaning you're now alkali or basic, you're going to want to bring that down to a level that's amenable to your plants that you're trying to grow. And that would take elemental sulfur to do so. Hopefully I answered that question. I think this graphic really solidifies the concept of what I'm trying to talk about. And they call it buffering capacity. So you're going to take soil samples and you're going to send them into a lab, and they are going to quantify what I was just talking about. They're going to give you a pH value, but they're also going to talk about, or they're going to give you a soil buffer pH, there we go, value. If your soil is acidic, they will not give you a buffer value if you're basic. They will give you a different rating, and they will call it excess lime, meaning you're above the threshold for pH of 7 or 7.2. So why I like this graphic so much, think of it as the old, well, they're not old, we use them all the time. They're percolators, coffee pot. And that is, you have this indicator gauge, which is your pH. And this large tank over here is all the nutrients, the hydrogen ions stuck to your clay particles, and this is your reserve acidity or your buffer. So when you pull out on the spigot and you start to fill your cup up with coffee, I hope you're following my analogy here, the indicator gauge goes down because it's reacting to what you're imposing. But as soon as you let up on that lever, what was in the tank now starts to immediately equalize and refill that. And so it's this kind of process that it takes to deal with soil pH. I do believe I gave you these tables, but and they should be just as valid in 1984 as they are in 2017. This is strictly soil chemistry stuff. It does not need to be revised according to these principles. And this is just in general, very general, what it would take to raise the pH to 6.5. No table. Panhandle is really angry at me right now. Sorry, guys. I will get you everything, I promise. I'm not trying to laugh at you. I realize this could be a little tricky if I didn't give you the right stuff. pH. If I'm trying to raise it from 4 to 6.5, that's a lot larger range than going from 6 to 6.5. So it would naturally take a lot more product to do so. But compounding that was what we were talking about with the soil texture. So if you went from sandy soil, let's just look at pH of 5. Let's look at this middle row. It would take roughly 6.5 pounds per 100 square feet of lime to raise that soil pH up to 6.5. But it takes up to 15 pounds to do the same change in pH, but on a clay soil, because it has such a large reserve tank of acidity that needs to be changed. This is pH, but the same concept will come up when we talk about, what if I have a lot of sodium in my soil? That's a situation that takes a similar approach to correcting as it does what we're talking about here with pH. And as you'll see, there's some soils that I'll present to you today that absolutely have to deal with these issues. Okay, the same concept, just inverted, if you want to think about it that way. And we're looking at a different scale now. We're looking at pounds per acre because this was taken from a commercial production extension publication from Cornell University. So they do everything on the acre basis because it's production ag. It's a lot larger. But we can still boil it down, and I'm going to show you how to do that during our calculations to the square foot area that would be realistic for growing and dealing with the garden.